Hello and welcome to today's video. We have recently introduced Taylor polynomials, and before we investigate the theoretical properties and the approximation properties of Taylor polynomials for certain classes of functions, let's have a look at a few quick examples first. So this section is called Taylor polynomials examples. And it consists of basically two examples. The first one is of a qualitative nature to get an idea of how a Taylor polynomial would look like graphically. Let's say we have a function f, so we consider f as given by a graph, and I'll sketch the graph below in just a second. The task will then be to sketch a few Taylor polynomials. Specifically, I'd like a Taylor polynomial of degree 0. Let's say we anchor that at the point -2. I want a Taylor polynomial of degree 1. That should be anchored at the point 2. And I want one of degree 2, and I'll anchor that at 0. So let's have a look at a possible example graph here. Let's say here's 0, here's 1, here's 2, -1, -2. So those are the important x coordinates here. And let's draw an example function. Let's say the function may look like something like this. And now we want to draw these Taylor polynomials. We'll start with this one of degree 0. So a polynomial of degree 0 is just a constant function at the point -2. This is here. So what we do is we just have a look at the function value at that point. This one here. And then t0 agrees with f in function value at x star, and that's it. It's a constant function with that value at x star. So t0 is going to be this function here. So that is t0. Now if we look at the affine linear approximation next, so t1 you remember is the same as the tangent. So at the point 2, this is this one here, we have this point here, and t1 is then the tangent to the graph at this point. So that function will look basically like this. Okay, so this is our t1. And finally, let's also sketch t2. T2 is a quadratic function, a polynomial of degree 2 that locally approximates our original function, in this case at the point 0. So 0 is here. Basically, we'll get a quadratic approximation at that point. Now let's say f is not per se a quadratic function. Otherwise, of course, the Taylor polynomial would be the same as the original function. But let's say it's not, so it's really just an approximation here. Then we get a quadratic function that looks locally similar to f, and that could look like this. Yeah, so it's just an artistic rendition here, that t2. But qualitatively, it will look something like this. Okay, so that's the idea of approximating a function through Taylor polynomials. And for the second example, let's also have a look at an actual quantitative example where we compute a Taylor polynomial. And the task here is we want to compute Tnf x centered at 0 for the function f, r to r, f of x is defined as the exponential function at x, so e to the power of x. Now what we have to do is, of course, we have to evaluate the function at the center point at x equals 0. And then we have to compute the derivatives of the function and evaluate those. So first thing we need to do is compute f at 0, which is e to the power of 0, which is 1. Then we need to compute the derivatives. And of course, f prime of x is again e to the power of x. So that's easy to do. And that also means we can compute arbitrary derivatives. So the nth derivative, or the kth derivative, that's the kth derivative of f at a point x will again be e to the power of x. That just reproduces. So that's a particularly simple function as far as derivatives are concerned. And sure enough, we can also evaluate those at 0. So that is again going to be e to the power of 0, which is 1. And same thing here. The kth derivative at the point 0 will again be e to the power of 0, which is 1. So all in all, you can conclude that our Taylor polynomial here is the sum from 0 to n of 1, and that is the fk at 0, right? That's just 1, over k factorial times x minus 0 to the power of k, or a little more concisely, the sum over x to the power of k over k factorial. So this is the Taylor polynomial of the exponential function, of the e function, for arbitrary degrees. Okay, so that's an example, and of course, usually it's not that simple to compute the kth derivative here, so you'll probably have to put in some work to get that. But once you have that, the rest is just substituting the result into that formula, and you're good. So that concludes our first round of examples. In the upcoming videos, we'll then investigate the approximation properties of the Taylor polynomials. And of course, we'll also see a few more examples for more complicated Taylor polynomials then. I'll see you then.